Okay, in fact, perhaps I should do that all the time, every time I have to clean the board and dry it, which is a waste of time, but perhaps I should just stop the filming before I do the job and then switch on again. Okay, so we're introducing a new concept now. You take a particular element of the group, well, any element of a group, so A belongs to G, and of a group, and then you generate all the powers of that element. And what I mean by that is like A. In fact, we'll start with E, and then A squared, and A cubed, and so on. And can you remember from the previous lecture the concept of the order, not of a group, that's just the number of elements in a group, but the order of an element. Can you remember that from previous lecture? So the order of an element is some minimum positive integer such that a to the k is just the unit. Right? Now, what is a squared? Well, it's just shorthand for a binary operator a. Okay, so a cubed is just a binary operator a binary operator a. Okay, so let's go up to k minus 1. Now, where k here is the order of the element a. Now, this e here, that's just a to the naught, right, by convention. Okay? Now, take all these elements and make a set out of them. And we'll call that h. Now you may say, oh, h? You mean, what we're going to do now is show that this set of all the powers of, and this is true for any element, right? You can take any element of your group and you calculate all its powers up to 1 less than the element's order. Okay? Now remember the distinction between the order of a group and the order of an element. It's unfortunate that the same term is used for both, but it's set in stone now. It's hard to change because thousands and millions of mathematicians have learned this, so it's sort of too late to change. Anyway, so you create this set here, and you take these powers up until 1 less than the order of the element, right? This, and so this here is a to the naught. Okay, so you'll have here k elements in your set. Okay? Now, this is so well known in group theory. It has its own special symbol, and it's this one. It's written like this, with angular brackets. So if you see this symbol in finite group theory, it's the, well, we haven't proved it yet, but it's referred to as the subgroup. This is what theorem 22 is about, proving that this set here that consists of all the powers of that element A. It doesn't matter which element in the set you're talking about. The same kind of analysis will go through. Each element, an element may have a different order than other elements in the group. That's possible. So the size of this set, might be bigger or smaller, depending on what element you've taken arbitrarily from your group. Okay, so this set here is actually a subgroup of G. Now, I suppose first thing, let's prove that this set here is a subset of G. Is that sort of obvious to you? Now G is closed, right? It's a group, right? So it has to have closure. So each of these members of H, or this subgroup, they all belong to G. Is that sort of obvious if you think about it? Like A belongs to G, right? Now G is closed, right? So A times A, whatever it is, must also belong to G, because that's what closure means. So this belongs to G. So A times that's A cubed, must also belong to G, because it's closed, and a similar logic all the way through, right? So this set here must be a subset of G. Hope you followed that. If not, rewind. Okay. So A here is a subset of G. Okay. And that's a consequence of the closure of G. Each of these has to belong to G, right? And so you've got this. So if this set, if the elements in this set, if each element in this set belongs to this set, because a group is still a set, right? So if each element in this set belongs to that set, then by definition, that set, which is this one, is a subset of G. Okay, so we've established that this set here is a subset of G. So we've started. Okay, now we're trying to prove that this H here, or this, same thing, is a subset. Sorry, subgroup is a group. Is a group. We've shown that it's a subset. So now, if we can show that it's a group, therefore it's a subgroup. Okay. Now, to prove that it's a group when it's a subset of G, we inherit the associativity. Okay, so we don't have to test for that. Usual thing. All right. So let's test these powers here. Are they closed? How would you do that? Well, let's see. So let P and Q belong to A or H. So, H. So prove that PQ belongs to H. If we can do that, for all P and Q, for any two elements in this set, in H or this same thing, all right? Well, look, P is just some random element from this set, so it'll have the following general form. It'll be something like that, right? Some power. It has to be, because this set is just all the powers of the element A. Okay. And there's a finite number of them, because every element has its order. Every element has its order. And if you're talking about a finite group, all those orders must be finite. They can't be infinite, because the group itself is finite, right? Okay, so P is of that form, and Q will be similar. So all right, call something like that. All right. Well then, PQ. Then it's just ARAS, and that's just A to the R plus S. Okay. Now, if this A R plus S is larger than the order of A, you can knock it down. So if R plus S is bigger than K, the order of your element, then you can subtract K. Now that won't change anything. Why? Because I'll express it a little differently. So if R plus S is larger than K, then rewrite this. Write R plus S as K plus, I don't know, something else, right? So so then A of R plus S is then A of K plus T, which is A of K times A of T. Now A to the K is just E, right? So this just becomes A of T. Okay? And this T is one of these numbers. Alright? Follow that? So that means that the product, P binary operator Q, or just PQ, is of this form. It's one of these. So the result belongs to your set H, or this. Okay? So it's closed. Alright. The unit, well, the unit's just this one, right? A to the naught. Right? Any element to the naught is just the unit. So, and that's in this set, right? So the E belongs to H. So we have the unit. And our inverses how to do that. Okay, so I'll say M. So M is just any member of your set here. So it will be of the form A to the I, let's say. Okay. Now the inverse. I'll just throw this at you. Maybe it's not quite so obvious, but let's say the inverse will be of this form. K minus I. Can you see where I'm going with this? So I'm just suggesting that the inverse of this, whatever this is, the inverse will be whatever this power is. You subtract that from K. Okay, now multiply these two. So multiply these two. So M inverse will be A to the I times A to the K minus I. Right? Well, that's just A to the I plus K minus I. And so that's, the i's cancel, so you're just left with A to the K, but that's E. Right? Because K is the order of the element. It's the order of A. This is just this. Okay? So M times M inverse gives you the unit. And if you do it the other way, it's just the same thing, because this is associative. Alright, so this, for any element belonging to this set, the inverse is of this form. So you just take this power, whatever it is, negate it and make it minus and add K. And that K minus I becomes the power of this A, and that's your inverse. So we've proved the inverse. Okay? So we've proved all three. So this is a group. Okay? And we proved earlier that it's a subset. So if it's a subset of G and it's a group, and we know that G is a group, therefore this H, or this, same thing, is a group, a subgroup. So this is a subgroup. Okay? No. We just, yeah, so we proved that was proof of theorem 22. Right? Now I'll stop and then start on the problem solving.